In this session, we'll look at how time affects digital logic circuits. Previously, we've looked at the gates that we can use to create any digital circuit. The three basic gates we have are the inverter, the OR gate, and the AND gate. Let's take a look at these first. If we look at the inverter, we can see that its output is going to be low, indicated by the bubble here, anytime its input is high. We look at the OR gate, its output is going to be high anytime any of its inputs are high. And finally, the AND gate is going to be high anytime all of its inputs are high. With our universal gates, we have two. We have the NOR gate and we have the NAND gate. With the NOR gate, we can see that its output is going to be low anytime any of its inputs are high. And with our NAND gate, we can see that its output is going to be low anytime all of its inputs are high. As long as we understand how each gate behaves at any instant in time, we can figure out how a circuit will behave over time. Let's look at an AND gate. So we have A and B. We know that an AND gate is going to output a high anytime both inputs are high. So if we look across here, the first time that we have both inputs high is right here. The next time they're both high is over here for these two time periods. And that's it. So if we want to draw our waveform in, we're going to stay low until both inputs are high, which is right here. We're going to stay high as long as both inputs are high. So A drops off here, so our output's going to drop down. A goes back high, B is still high. So over these two time periods, the output's going to be high. And then it's going to stay low until the end. Now if we take a look at another example, this time let's do A or B. So this time we're looking for A to be high or B to be high in order for our output to be high. So as we're going along, we can see that here A goes high and it stays high. B changes, but A is already high. Now B stays high, so our output's going to stay high. A is high after B drops down, so our output should stay high until here. Here we have a very short period where both A and B are low, so our output should go low. Here B is high again, so our output will go high, and finally we'll drop down and end with a low because they're both low here. So let's draw that one in. So A goes high first, our output goes high. B joins it, doesn't affect it at all. Here A drops off, but B is still high, so we're going to continue on till our next change. They're both high here. B drops off, but A is still high, so our output stays high until here. Now we have them both low, so our output's going to go low. We come across, B goes high, it's at least one of the inputs, so our output goes high, but they both are off here, so our output will be low. Let's do one more example. This time, let's do A naught ANDed with B naught. So in this case, both of our inputs have to be low in order for our output to be high. So let's take a look in our waveforms. Both of them have to be low for our output to be high. So in this case, we're going to start with a high. Then the next time they're both low is way over here. So we have two time periods over here where they're both low, and then the very end. So let's mark those in first. So we have them both low here, our output's going to be high. They're both low over here, our output's going to be high, and they're both low in the last time period, so our output's going to be high. Then I'm going to go back and I'm going to fill all the rest of the time periods in as low, because we've taken care of the cases where it's otherwise. Now if you look carefully here at these last two waveforms, you can see that they're the opposite of each other. So we have A or B as the first one, and the other one is A naught, B naught. Now if you think about that and you apply De Morgan to it, and let's De Morgan this side, we can see that we have A naught, B naught. We're going to change the gate. We're going to invert the inputs, and we're going to invert the whole thing. Then we eliminate any double bars, so we now have A or B inverted, which explains to us why these two waveforms look to be the inverse. We have an OR gate here and we have a NOR gate here. Now let's take a look at a circuit that's a little more complex. We now have three inputs, A, B, and C, a few more gates, and we have one output still. Now, we could take our time, and in our timing diagram we could work our way through based on waveforms for A, B, and C. We could look at what happens after this inverter, after this AND gate, after this inverter, after this NOR gate, and then finally combining these two gates together, what our output would be at X, which would take a lot of time. So what we're going to do instead is we're going to use our bubble matching technique to figure out how our circuit behaves. Now remember, with our bubble matching technique, we want to make sure that each wire has the same state at both ends. So here we have a high state here and a high state here. So that's good. But on this one, we have a low state here and a high state here. So we need to do some De Morganing, if I can use that as a word, to ensure that both those ends are correct. So it would make sense to correct this one. So what we're going to do is we're going to replace this gate, the NOR gate, with its De Morgan equivalent. So I'm going to eliminate this, and what we're going to do is we're going to replace the gate itself. So it was a NOR gate before, so we replace that with an AND gate. We invert each input, so it had highs going in, so we get a bubble on each end here. And it had a bubble on the end, so it doesn't have anything now. So we now have the De Morgan equivalent to our NOR gate, which is an AND gate with inverted inputs. Now we have one more case here. So if we look here, we have an inverter and a bubble. So what we can do is we can eliminate that inverter and we can eliminate that bubble. So let's, for a little clarity's sake here, let's get rid of that, get rid of the bubble. And let's put the line back in there. So we now have a circuit that looks like this. Now, we can read our logic from this. We know that our output is going to be low because of the bubble here. So we're going to say that the output is low, and then it's dependent on the two paths we have, this top path and this bottom path. So the top path is dependent on C being low at the same time that A is high. So let's put that part in. So A has to be high, and C has to be low. Now if we look at the bottom path, we have A is high, and B, because of this bubble right here, has to be low. So that's the condition for our second one. So here, A is high, and B is low. Now the last thing to look at is the condition that we have based on our final gate. Now this is an OR gate, actually a NOR, but we've looked after the bubble already. So what we're going to have as our joining condition here is OR. So now we know that this circuit is going to be low anytime A is high at the same time that C is low, or anytime A is high at the same time that B is low. So let's take a look at that. So here we can see waveforms for our three inputs, A, B, and C. What we need to do is figure out, based on the logic we just figured out, which is defined up at the top, how our output is going to behave. So our output is x, so we'll mark that in. And then what we'll do is, because we have an OR condition here, what we're going to do is we'll look after the first part, and then we'll come back and we'll look after the second part. And if either of those are true, then our output will be high. So let's look at the first one first. So it says A is high at the same time that C is low. So let's go through and identify those. So A is high for these 3 time frames here. Is C low? Yes, it is. So our output is going to be low during that point. So let's mark that in. So for these 3 time periods here, A is high at the same time that B is low. Now, let's see if there are any more. So A is high for this period right here. Is C low for any of that? Yes, it is right here. So what we're going to do is mark that period of time in as a low. Do we have any more time periods where A is high and C is low? As we move along, A is high for these 2 right here, but C is also high, so that doesn't qualify, and that's it for A being high. So based on the first condition, X will be low for those 5 time periods. Now let's look at the second one. So in this case, A is high at the same time that B is low. So if we look through, A is high for these 3 time periods, B is low for 2 of those. So that would mean our output would be low for these 2 periods. We already have it marked there from the first condition. So let's continue on. A is high for these 5 periods over here. B is low for 3 of those. So let's fill those in. It's these 3 time periods here. It's already low for 1 of those. But we can see now that we've marked in all the conditions for the first part and the second part, so we've now completed. Let's fill in the rest of our waveform. We know that every other period of time our output is going to be high. So we come through, let's make this one a little neater, and that's what the output for our circuit is going to be over the period of time defined here for the inputs that are defined. So in summary, when we're given a timing diagram that shows the input patterns for all of our inputs, we're able to define over a period of time how our output X in this case is going to behave based on our input waveforms.